yesterday I gave you an introduction to some of the modern methods of analyzing the partial differential equations, and today I wanted to continue that and some other tools, basically tools from calculus of variation. Okay? So let me begin. So maybe I will give the title as calculus of variation.
Recording in progress.
So to motivate, I just wanted to start with something which you people might have already seen, what is known as the Differential principle. Differential principle. So consider the problem. And so the problem or the PDE, okay, minus Laplacian of u is equal to, say, f of x in some omega, and with u is equal to g on boundary of. So what is given as, you have a domain, this is omega which is given, and f from say omega to r is a function which is given, and g from say boundary of omega to r. These are all given quantities. So now the question is to find a u which satisfies Laplacian of u is equal to f and u is equal to g. This is what is known as the Differential problem. So I am sure you must have already discussed some cases of this. Okay. Now, suppose I am trying to find a solution of this. First of all, the solution has to be twice differentiable because I have to talk about Laplacian. So that means the second derivative should exist. So I am going to take a class of functions which I call it as script A is equal to u, set of all u, which maybe I will call it as all function in C2 mega closure, so that I can talk about Laplacian of that. Okay? And then I will also say that it has to satisfy the boundary condition u equal to g on boundary of it. So I am considering all twice differentiable form. Anything?
Hello.
Hello? Hello, is there any issue?
Hello.
Okay, yeah. So I am defining script A is equal to all u in C2 of omega, okay, such that u is equal to on the boundary. Okay. So now the question is, I am going to call this Differential problem I am putting as number 1. Then we know that solutions of 1 are, say, elements of A satisfying Laplacian of u is equal to. Now, so what I wanted to do is that so what does the Differential principle says? Okay. Now I have to, so the script A is this class of function, that means all twice differentiable functions, which is equal to g on the boundary. Okay. Now I am going to define something called an energy. Okay. I am going to call E, define, say E from my class script A to R by define E of u, that's going to be equal to half of integral over omega gradient of u square minus integral over omega fixed into. So, for example, this equation 1, which comes in various contexts. okay, so various physical contexts, and you can write an energy corresponding to that, for example, and this coincides with that kind of a physical notion of energy. For example, you can see the first term as kind of a kinetic energy and the other one as a potential energy whenever that is the context and so on. Okay. So, yeah, so this kind of situation, you have an energy defined. This is for all UE. Then what is the Dirichlet principle? So, which is the Dirichlet principle. So the Dirichlet principle says that, so U naught, so a function U naught element of script A is a solution of the Dirichlet problem. Dirichlet problem 1. What is 1? 1 is this equation. Laplacian of U is equal to F and U is equal to G on the boundary. Okay. So a function U naught is a solution of the Dirichlet problem 1 if and only if U naught is a minimizer of the energy. That is, what does it mean? That is, if and only if E of U naught is less than or equal to E of U, okay, for all U in. That means the solutions of that PDE is a solution of U naught is a solution of that PDE if and only if that minimizes the energy. Okay? So this is the Dirichlet principle. Okay? It's also connected with all these least action principle, which tells you that a system tries to minimize the energy and so. So I'm not bothered about any of those physical aspects. Okay, so I'm just now looking at it purely as a mathematical problem. Okay, so I will just give you a proof here. Okay, it's not very complicated. So let's say that a function U naught is a solution of the Dirichlet problem if and only if U naught is a minimizer of the energy. This is what I wanted to prove. Okay. So let me just try to prove it. Okay. So first, let's assume U naught solves the PD. That is, what we have is U naught solves the equation minus Laplacian of U naught is equal to F in omega, and U naught is going to be equal to G in omega. Okay. Now what I wanted to show that, we want to show that U naught is a minimizer. So that E of U naught is less than or equal to E of U for all U element of script A. Now recall the script A. What was that? Yeah, so say all U in C2 such that U is equal to G on the boundary. That is the definition of script U. Okay? So this is what we wanted to prove. And it is given that U naught satisfies this differential equation. Okay? Okay, so let me take an arbitrary U. So let U element of script. Okay? And then consider U minus U naught. Or let's consider then U naught minus U. Okay. So this is in C2 of omega closure, and u naught minus u, this is going to be equal to 0 on boundary of omega. On boundary, both u naught and u are is equal to g. So therefore u naught minus u on the boundary is g minus g, and that is going to be equal to c. Okay? So this function. Now I know that u naught satisfies the equation minus Laplacian of u naught is equal to f. Okay? So what I do is that I am going to multiply this with this quantity u naught minus u. Okay? And I will multiply right hand side also with the u naught minus. Now after that I am going to integrate this both sides over the domain. Now let us try to simplify this. You can apply the integration by parts here, and so then when you apply the integration by parts, what happens is that left hand side becomes integral of omega. It will become gradient of u naught dot product with gradient of u naught minus u, and on the right hand side you will get integral of omega f into u naught minus integral of omega f into u. Okay. Now let's simplifying further, the left hand side becomes integral of omega gradient of u naught square minus integral of omega gradient of u naught dot product with the gradient of u. That is going to be equal to integral over, say, f of u, f into u naught minus integral over omega f into u. Now I want to show that energy of u naught is less than or smaller than energy of u. So u naught, so let me rearrange it. So this implies that integral of omega gradient of u naught square, okay, then plus minus integral of omega f into u naught. Okay. So on the right hand side you will have integral over omega gradient of u naught dot product with gradient of u minus integral over omega f into u. Now on the left hand side it looks like more or less like energy modulo a fraction 1 by 2 is missing. So let's recall what is energy. Energy is half of integral over omega gradient of u square minus f of u. Okay. So the left hand side is, if I have a 1 by 2 here, then it is going to be an energy. And the right hand side looks little different. It is not exactly that. So what I do is that I will use the Cauchy-Schwarz inequality. Okay. So then you will get that this is less than or equal to integral of omega gradient of u naught square to the power 1 by 2 into integral of omega modulus of gradient of u square to the power 1 by 2 minus integral over omega x into u. Now you know that AB is less than or equal to a square plus b square by 2. So using that you will get this is less than or equal to 1 by 2 integral over omega gradient of u naught square plus integral over omega modulus of gradient of u square, okay, then minus integral over omega f into u. So once I have that, so now you have a half gradient of u naught square and a gradient of u naught square. I can push this to the left hand side, and this will imply that half of integral over omega gradient of u naught square and minus integral over omega f into u naught. That is going to be less than or equal to half of integral over omega gradient of u square minus integral over omega F into, and that is what we have is the energy of U naught, E of U naught is less than or equal to E of U. And this implies that U naught is a minimizer. Yeah. Okay. So what we have proved now is that if U naught is a solution of this Dirichlet problem, then U naught is in fact a minimizer of the energy. Okay? Now we want to prove the converse. So I am going to assume that conversely, assume that U naught is a minimizer of U, minimizer of E in the class A. Okay? That is what we have is E of U naught is less than or equal to E of U for all U in state. Okay? So we want to show that U naught solves the PDE. What? Okay. So U naught is in the class A, so therefore you know that U naught is equal to G on the boundary. So it is enough to show that U naught satisfies the differential equation, that is minus Laplacian of U naught is equal to F. That's all we wanted to show. Okay. Okay, so let us try to do that. Okay. So E is a minimizer of the energy. This is what I have to use. So what I am going to do is that I am going to start with let phi element of Cc infinity of. That means, so I have a omega is this, okay. Phi is a function which is on some compact subset only, it is non-zero, and it will vanish near the boundary, and it's a C infinity function. I will fix such a function, okay. And for t element of R, any real number, consider U naught plus t times, okay. Then this is in the script class. U naught is a C2 function, phi is C infinity, so U naught plus t phi is a C2 function. Okay. Now U naught is equal to G on the boundary, and phi is going to be 0 on the boundary. So U naught plus t phi is going to be G plus 0, that is equal to G. Okay. So that shows that U naught plus t phi is infinity. So now I define a function F, define a function, say H from anything?
No, I think by mistake someone had.
So define H from R to a function H from R to R. I can define by H of t is equal to, what I do is that energy of the function U naught plus t times t. Okay. So this is a real valued function, and then you see that, for example, E of U naught is a minimizer of the energy. So this implies that t is equal to 0 is a minimum of. Okay. So 0 is a minimum of the function h. So you know that from the standard calculus, this implies that h derivative at 0 will be 0. Okay. So let us try to see what it means. That is, that is d by dt at t is equal to 0 of what? The energy, that is E of u naught plus t phi, that is going to be equal to 0. Okay. Let me expand this. That implies that d by dt of at t is equal to 0 of the energy is nothing but half of integral over omega modulus of gradient of u naught plus t times gradient of phi all square minus integral over omega f into u naught plus t times phi. So this is what you want. We know that this derivative is going to be. Now when you differentiate the first one and evaluate at t equal to 0, what you will get that this is going to be equal to integral over omega gradient of u naught dot product with gradient of phi. Okay. It's a direct differentiation. You can differentiate under the integral sign. It can be justified. And then this quantity, when you differentiate, you are going to get gradient of u naught dot product with the gradient of phi. Okay. And on the right hand side, you will get that is minus integral over omega f into phi, and that is equal to. Okay. Now you know that u naught is a C2 function and phi is a C infinity function with compact support, and this I can further reduce to say minus. I can use integration by parts to change the first one in Laplacian of u naught, this into phi minus integral over omega f into phi equal to. And this implies that integral over omega you have Laplacian of u naught plus f, this into phi equal to. Now note that I have started with an arbitrary phi. So that means this conclusion holds for all phi which is in Cc infinity of. That means you have one function here and you integrate that by multiplying with any C infinity function with compact support, and then as I pointed out yesterday, so this will imply that that function Laplacian of u naught plus f is equal to 0, or equivalently which is minus Laplacian of u naught is equal to f. This implies that the u naught solves the or the Dirichlet problem PD1. Dirichlet problem says that Laplacian of u naught is equal to f, and also you should have u naught is equal to g. Since u naught is in the class script A, these are all functions which are C2, and that is going to be equal to g on the dot. Okay. So this shows that this proves the Dirichlet principle. Okay, so what is the Dirichlet principle? Let me just recall once again. Yeah, it says that u naught solves the partial differential equation or the Dirichlet problem if and only if it's a minimizer of the energy. Okay. So this is the one. Now, I just want to have a closer look at the problem. Okay. So especially the second part, I assume that u naught is a minimizer, and from that I concluded that u naught is going to be u naught is a minimizer, and from there I concluded that u naught solves the partial differential equation. So how did I do that? I defined a function h from R to R, and h of t is equal to e of u naught plus t phi, and then I just differentiate. Okay. So this basically is nothing but the directional derivative of the function in the direction. Okay. So in finite dimensions, for example, if you want to find some df by some dv, what you do is that d by dt of f of x plus dv, and you differentiate. Okay. You differentiate along that direction. This is something similar. So in fact, finally to conclude that this it solves the equation, I did not really use the fact that it's a minimizer. what I used is that only this derivative is 0. Okay? And in fact, it is indeed true that the solutions of many of these kind of partial differential equations can be obtained as the some derivatives of, or the derivatives from the derivatives of some of this energy. Okay? So for that, first of all, I have to talk about, so this E function looks at this E. I have defined it in the very beginning. Okay? E is here, I have defined. Okay? E is defined from this script A to R. Okay? So this is a function space, and you are taking a real valued function. So what is the derivative of such a function? So you can define the notion of derivative of such a function and then connect it with the notion of solutions. Okay? Now these are all infinite dimensional spaces. For that, I have to introduce the notion of what is the derivative of a function from a Banach space to R. Okay? So that is what I am going to define next. Okay? So this is what is known as the Frechet derivative. Frechet derivative. So let me start with, let X be a Banach space, and U be an open subset of X. Open subset of X. And let me take its F is from U to R. Then F is said to be differentiable. Differentiable or Frechet differentiable. At the point x naught element of U, if there exists a L element of X star, it's the dual space of X star, such that it's not f of x naught plus h minus f of x naught minus L of h modulus of that divided by norm of h, and this goes to 0 as h goes to 0. Okay. So this is the definition of derivative of a function which is defined on a Banach space. Okay. So the thing is that you have a Banach space, okay, and you have a subspace. This is an open set U, and I have a point x naught here, okay, and I have a function defined from here to R. This is the function capital FHST. Okay. So we will say that f is differentiable or a Frechet differentiable at the point x naught if there exists a linear transformation from the domain to the range. That is, domain is U. So the full space is the Banach space. Right? So that is why I have written L is an X star. That means there is a bounded linear functional from X to R, such that this relation is true. That is, f of x naught plus h minus f of x naught minus LH is equal to norm of x. So this definition can also be seen as this is also equivalent to saying that you are basically, what you are doing is that, you see, the function f of x naught plus h, that you are basically approximating it with f of x naught, this is a constant, plus L of x. Essentially what we are doing is, we are approximating f near x naught by a linear transformation plus some. And how do you make sense of that error? This is the way what we have written, that is what is the error. Okay? Or in other words, error can also be, it is written in the form something which when you divide with an OMH, that should go to 0. Okay? This is what the differentiation is all about. Okay? So I can give you some, so you can prove that. I will just write it as a remark. So this is very similar to, for example, I have defined the derivative of a function f from x to r or u to r. There is nothing special about r. Even if you have a function f from u to another Banach space y, you can give the definition in the same way. Okay, in that case, the derivative is going to be a bounded linear map from x to y. That is the only change. So this is just a generalization of the, you must have seen the derivative of some mappings from Rn to Rn. Okay? There you define the derivatives as linear maps from Rn to Rn. Okay? And they are finite dimensional spaces. They are all linear maps are continuous. Okay? So here X may be an infinite dimensional space. That is why we have to make sure that we assume that in addition they are going to be continuous linear functions. Okay, that is, continuity has to be specified. That's okay. So this is the thing. So I say that if f is differentiable at x naught, if there exists a linear bounded linear map L, or L is an x star, such that this satisfies. Okay. So it is possible that there may be more than one such, this condition may be satisfied for say two functions, L1 and L2. We may suspect that. Okay? But it is not true. And if such an L is possible for at most one such L. Okay? So that's what I wanted to bring. So in the definition, of derivative, okay, the L element of x star, okay, if it exists, the element of x is unique if it exists. If it exists. Okay. So the unique L, if it exists, is called the derivative or a pressure derivative. Derivative or pressure derivative. Derivative of capital F at x naught. Okay. We will denote this derivative, this unique L by df at x naught. Okay. So that is df x naught. So df at x naught, this is an element of x. Okay. So derivative, if it exists, it's going to be in the dual space, and that is going to be, so for each x naught it will be different elements if it is differential. Okay. Now, so I will give you a definition. If x naught element of u is said to be a critical point, critical point of f if TF of x naught is equal to 0. That means x naught is said to be a critical point if its derivative at a point is going to be 0. Okay? So let me give some examples, some small example. I don't have much time to do many things in detail. So let's take some example. Okay? So let's take a function capital F from say R2 to R. Okay? So this is a finite dimensional example. I am going to take capital F of xy is equal to say, let's take some x square into y. So let us try to find what is the derivative. Okay, I wanted to find the question is about what is df at x naught y, whether it will exist or not. So if at all it exists, it has to be a linear map from R2 to R. Okay. So we wanted to check. So the question is, does there exist an L such that modulus of f of say x naught y naught, this is the point, plus h I put it as some h1 h2, okay, minus f of x naught y naught, okay, minus L of h. Okay, that is L of h1 h2. Okay. And then this modulus divided by norm of h. This should go to 0. Okay. This should go to 0 as h goes to 0. The question is what? So we know that this quantity, we know this quantity. Okay, so first let us try to expand that. What is f of x naught plus h? X naught y naught plus h1 h2 minus f of x naught. Let's try to see what it is. So this is going to be f, you know the definition, that is x naught, this is going to be x naught plus h1. Okay, so it is x square y, this is into y naught plus h2. Okay, this is x square y minus, you will have x naught squared. Okay. When you substitute this, what you first one you expand, you will get x naught square, y naught, that will get cancelled. Then you will have here, some 2x naught y naught is into h1. Okay, you will have that. And then what are the other things you will have? Okay, let me explain. Write it. So this is going to be equal to x naught square plus 2x naught h1 plus h1 square, this into y naught plus h2 minus x naught square y naught. So this is what we have. And yeah, h1 square, this into y naught plus h2. Yeah, so when you simplify this x naught square y naught and x naught square y naught, that will get cancelled. So what you have is, you will have some terms which is like 2x naught y naught into h1 here. Now h2 will be there with plus x0 square, this into h2 will be there, h2 will be there. And then plus you will have terms like 2x naught h1 h2 will be there. Then plus you will have some h1 square into h2. So you can see that this is a linear functional in h, that is in h1 h2. So what I am going to call it as define L of h1 h2 is going to be 2x naught y naught into h1 plus x naught square into h2. Okay. So once you do that, then what you, this will imply, with this definition, then L is, then L is linear, L is linear, and what we see is that f of x naught y naught plus h1 h2 minus f of x naught y naught, okay, minus L of h1 h2. Okay. This is going to be equal to what we will be left with. This is something like 2 times x naught into h1 h2 plus h1 square into h2. Okay. So therefore this quantity, which entire thing divided by mod h, that's going to be modulus of this divided by mod h. Okay. So this I can write it as 2 times mod x naught into, so the above one I can estimate with by mod h square, and the other one I can estimate with mod h cube, and divided by mod h. And you will get that this is going to be 2 times mod x naught into mod h plus mod h square, and which will clearly go to 0 as h goes to 2. Okay. So therefore this implies that f is differentiable at x naught y naught, and the derivative is df at x naught y naught. So this is going to be a linear transformation. So this acts on h1 h2. That is going to be given by this one L. What is L was? Yeah, 2x naught y naught into h1, 2x naught y naught into h1 plus x naught square into h2. Okay, so this is the derivative. Okay, so then is x naught y naught is so this is a, so this linear transformation depends on x naught and y naught. Okay, so for example, what is df at the point, say for example 0 0, then x naught and y naught are 0, so therefore it implies 0. So this is a 0 linear transformation. This implies that 0 is a critical point. Okay. Now not only that, for example, I can assume that I can take any point, something like df at say 0 1 or 0 any y naught. So this is x naught is 0, then again this is going to be 0. That implies these are all critical points. 0 y naught is a critical point. Is a critical point. Critical point for any y naught. Any y naught. Okay. So what you see that this function has plenty of critical points. Okay. So this is a simple finite dimensional example. Now let me give you another example. Okay. Let H be a Hilbert space. Let H be a Hilbert space. Hilbert space with the inner product. Inner product, okay, and define a capital F from H to R by capital F of say x is equal to norm of x square, and that is nothing but inner product of x with x. Okay. And then we can try to find what is the derivative. So you can try to find the question is what is df at a point x naught. Okay. You can try to see. So you can do the same kind of things. For example, you can find say something like f of x naught plus some h minus f of x naught. You can calculate this, and then what you will get is here is norm of x naught plus h whole square minus norm of x naught squared. This is nothing but the inner product of x naught plus h and with x naught plus h and minus norm of x naught square. That's going to be equal to, you will have, assuming it's a real inner product space, then x naught, norm of x naught square will get cancelled. You will get 2 times inner product of h with x naught, okay? Then plus norm of h square. This is what it is. Again, you can see that this is going to be linear in h. Okay? So I will define, say, L of h is equal to 2 times inner product of h with x naught. Okay? So once I do that, then this will imply that modulus of f of x naught plus h minus f of x naught minus L of h, okay? Then divided by norm of h. Okay? That is going to be equal to, so once you subtract, what is remaining is something like norm of h square divided by norm of h, and that is going to be equal to norm of h, and that goes to 0 as h goes to 0. Okay? So that means this L is the derivative. That implies that df, derivative of f at a point x naught. This is nothing but, this is a linear transformation, so it acts on some h that is given by 2 times inner product of h with x naught. You can see that this linear transformation, as you vary x naught, it changes. Okay? And you can see that the only critical point of, so df x naught, so suppose x naught is a critical point for this. Critical point. So what does it mean? Suppose it's a critical point, then this will imply that df, by definition, this is df of x naught has to be 0. This implies df at x naught of h has to be equal to 0 for all h. Okay? This implies that inner product of h with x naught has to be equal to 0 for all h. In particular, this implies that inner product of x naught with x naught equal to 0, and that implies that x naught equal to 0. So this function, which I defined on an arbitrary inner product space as the norm of the square of the norm, and that is a differentiable function, and that function's only critical point is the function x naught equal to 0. Okay? So I've been talking about, now my main job is, you can have many examples, you can see many of the standard books for some of the examples, okay? And my main interest is, I want to connect it with the PDE, what we have been talking about, okay? So that is what I am going to talk about, okay? So this Fresher derivative, and so I want to write critical points and P. This is what I wanted to do. Okay. So morning I talked about only linear PDEs. Okay. So I'm going to talk about some kind of a non-linear PDE. Okay. Again, I'm going to start with the let omega be a bounded domain in Rn. It's a very nice domain. If you have any difficulty in assuming what it is, just take it as a ball in the Rn. Okay? And consider the problem. Consider the PDE. I wanted to consider minus Laplacian of u of this at x is equal to, I'm going to write something like an f of x u of x. This should be in omega, and u of x is equal to 0 for x on the boundary of omega, okay, where f is from x defined from, say, omega closure cross r and to r is a given continuous function. Given continuous function. Okay. So omega is a bounded domain in Rn, then the PDE, the Laplacian of u is equal to f of x ux in omega with ux is equal to 0 for x is in omega, and where f is a given function, it's a nice function which is given from omega, it is defined on omega closure cross R to R. Okay. Now, just like in the Dirichlet problem, I had defined an energy there. Here also I can define an energy corresponding to this problem. Okay? Define, maybe I will define E of u. The first term will be exactly the same, half of integral over omega, gradient of u square, okay, minus, I will write the second one as integral over omega, capital F of x, u of x, dx. Here also it is dx. So I will tell you what is this capital F means, where this capital F is the primitive of, yeah. That is what I wanted to tell you is that, yeah, f from is a given function, and also I assume that say f of x0 is equal to 0. I'm going to put that. Okay. So that's what I'm going to do is here is f of say some x t. I wanted to define this. This is going to be integral from 0 to t. Small f of x some s. That means in the last variable, so this implies that capital d by dt of capital F is going to be of x t is going to be small f of x. So I have this problem which is given, the partial differential equation, and correspondingly I am going to have an energy. Okay. So now the problem which I am talking about, it is like say minus Laplacian of u is equal to f of x u. This is a nonlinear term. For example, so examples you can see. So for example, you can take f of x comma u of x. This is, for example, this could be something like ux square. Or you can have, this is sine of ux. Okay. You can have various possibilities. You can have something like mod x into, say, e to the power u of x. You can have this. Okay. Like that, whatever you can think of, you can have that. Okay. The only thing is that f has to be continuous. So what I am saying that this is going to be a nonlinear problem. Earlier in the Dirichlet problem, it was only f of x. Okay. There was no u there. Okay, this u will depend non-linearly. That's what I am saying, it is a non-linear problem. Okay, so it's a very general equation what I have written here. Okay. And then once I have this, and then I have this energy. So now I have the energy I have defined here. Okay, and so then I can define this energy. Okay, so now the first theorem I can define. So let me define some Banach space. Let x is equal to, set of all u element of C2 of omega closure such that u is equal to 0 on boundary. Or C2 function which is 0 on the boundary. Okay. Now what I can do is that I can define a norm on x by norm of a function u is going to be supremum of, say, mod u modulus of ux, then you can put the modulus of uxi of x, okay, and the second derivative u is c2, so you will have all first derivative uxi xd. This is when x, the supremum over all x in omega, okay, and this is for I equal to 1 to n and j is equal to 1 to. So what I am saying is that norm u is nothing but the supremum of u, first derivatives of u and the second derivatives of. Then I will leave it as an exercise to show you that x with this norm is a Banach space. Banach space. Okay. Then the next thing I can prove as a theorem. It's a theorem, okay, which I won't do it and I will just state it. Okay. Let E from x to r be given by E of u is equal to half of integral over omega gradient of u square or gradient of u of x square dx minus integral over omega capital F of x u of x dx. Okay. I define a functions like this from x to x is a Banach space. Then E is differentiable. E is differentiable at any u0 element of x and the derivative of E at the point u0. This is an element in x star. Okay, x star is given by saying B at u0. This acts on any function phi that is going to be equal to integral over omega. So gradient of u0 dot product with gradient of phi minus integral over omega small f of x. Maybe I will write it. So this is going to be equal to integral over omega gradient of u0 dot product with the gradient of phi minus integral over omega f of x u0 of x, this into phi. Okay. This is true for all phi in, for all phi. So this is going to be the derivative. Okay. And once it is a derivative, so that's I can, as a corollary, I will see that suppose u0 is a point. Suppose u0 is a critical point. Critical point of okay. Then you know that dE of u0 is going to be equal to 0. This implies from the previous theorem, we know what is dE0. This implies that integral over omega gradient of u0 dot product with the gradient of phi minus integral over omega f of x u0, this into phi, this equal to 0 for all phi in x. Okay. This will imply that I can use integration by parts like what I did many times. This will imply that Laplacian of u0 plus f of x u0, this into phi equal to 0 for all phi in, say, cc infinity of omega. Because cc infinity of omega is also in x. Okay? So this will be here. This implies that you will have minus Laplacian of u0 is equal to f of x u0. So it will imply that it is going to be a solution of the PDE. So, or in other words, the theorem is that, okay, u0 is a solution of minus Laplacian of u is equal to f of xu in omega with u is equal to 0 on boundary of omega. This happens if and only if u naught is a critical point of length E, which is defined from x2. Okay. So with this theorem, our problem of solving the PDE reduced to finding the critical points of functions defined on Banach space. Okay. So we will talk about that in the next lecture, and I will stop here now. Okay. If you have any questions, you may ask or later. Now or later. Okay, we will see after. Yeah.
Just for a photosession data online and offline.
Yeah. Okay. Is it visible now, the screen?
Yes, sir.
Okay. Okay, so next I am going to take up the question of, so
Recording in progress.
So the main conclusion that I have arrived at in the morning session is that this problem, for example, u naught is a solution of certain PDEs, which we call it a semilinear elliptic type. Okay, and that problem is a solution if and only if u naught is a critical point of an energy or a function from a Banach space to R. Okay, so therefore, now the remark is therefore the problem reduces to finding critical points of functions, say maybe I will call it as J, from x to R, where x is a Banach space. So this problem is a general problem. Okay. So what we have seen is that critical points are critical points of in the previous theorem, critical points of the energy are precisely the solutions of the partial differential equation. So the question is, how do you find the critical points of a function defined on a Banach space? Okay. So this is a very general question, so which is applicable in many contexts and for many problems and so on. Okay. So this is what we are thinking about, right? Okay. So the first candidate for a minimum, for a critical point is a local minimum or local maximum. Okay. So for a function, we know that at a local minima, it is going to be, the derivative is going to be 0, and at a local maxima, it is going to be 0. So I have not proved it in this context, but you can argue exactly in the case of how you do it in the Euclidean case. And you can see that local minima and local maxima are the first examples of critical points. Okay? So the question is, so the question which I wanted to ask is that now let J from, so say x to R be a function which is differentiable. Differentiable at every, say, x naught element of x. Okay, and suppose J is bounded from below. Below, say J of x is greater than or equal to some m for all x in x. Okay. So the question is, does J admits its minimum, its infinite? Okay. That is the question is, that is, so let me let infimum of J of x element of x, this is going to be, I am going to call it as some number. Okay, since it is bounded from below, so this has to be greater than, strictly greater than minus infinity. So the question is, does there exist an x naught element of x such that J of x naught is going to be this infimum value? So that is so we want to see whether this infimum is going to be attained at a point x naught. That is what we wanted to see. Okay. So let us look at this question. So whenever we want to see whether an infimum is achieved, one of the natural thing is you try to take a sequence which converges to that and then see whether we can conclude something. Okay? So let me choose. So let xn be a sequence in x such that J of xn, the sequence J of xn, this converges to M. Okay? Since it is an infimum, there will be a sequence such that J of xn converges to M. Okay? Now, next I am writing it, suppose xn has a convergent subsequence, say some x in I which converges to some x naught. Okay, then see, so then we know that then J of x n I, since this also will converge to, okay, now, so but x n I converges to x naught. So if I can, whether x n I converges to x naught, can I, does this imply that J of x naught is M? For that we need, what we needed is, if limit I goes to infinity, J of x n I is equal to J of limit of x n. That is, if J is continuous at x n. Continuous at, okay. So what, there are two things. If xni, if xn has a convergent subsequence, and if J is, so the final message is that, okay, if xn has a convergent subsequence, and j is continuous at x naught, then the infimum x, then the minimum is achieved. Okay. So there are two things. There are two things involved. One is extracting a convergent subsequence. And the second one is the issue of continuity. If I have these two, then I can then I can show that the j will attain its minimum, and therefore it is going to have a critical point. Okay. So now how do we? So first look at that first property. This extracting a subsequence. This is a compactness property. Okay, of the Banach space. Okay. Now you can see that it is not that easy to. So it is not very easy. One has to deal with compactness in an infinite dimensional space. Okay. So for example, if you are in finite dimensional spaces are locally compact, and so this implies that if xn is a bounded sequence, then it has a convergent subsequence. Okay. So if a bounded, so in a finite dimensional space they are locally compact. Therefore, if xn is a bounded sequence, then it has a convergent subsequence. But in PDE applications, X is set function space. X is some function space, and it is infinite dimension. Okay. So you know that infinite dimensional spaces, which are not locally compact. Okay. For example, you can have bounded sequences which may not have convergent subsequence. Okay. For example, you can give this example. I can give you the space little l2. Okay. These are all sequences xn. Okay. Such that sigma xn square is finite. Okay. Then you can take the sequence. For example, you can take a sequence. Consider the sequence. So the first element is say 1 0 0 etc. Second one is 0 1 0 0 etc. In general, the nth one is 0 0 etc. 0 and 1 0 0. You can take these kind of sequences. You can see that the distance between any two elements is something like root 2 or something like that. Okay, so this distance between any two members is a definite positive number, and there is no convergent subsequence for this sequence. for this sequence. So this is one of the main difficulty. We may not be able to in an arbitrary Banach space, okay, and given a sequence, even if it is bounded, you may not be able to find a convergent subsequence. Okay, but in Banach space theory, if you learn the functional analysis, there is a theorem which is kind of a little bit of a substitute for it. Not exactly is the same. There is something called a weak convergence. Okay. And there is a result which tells you that if the space is reflexive, then for any bounded sequence you can extract a weakly convergent subsequence. Okay? So I will just recall this theorem from functional analysis. Theorem which tells you that let X be a reflexive Banach space. Okay? Reflexive Banach space. Let X be a reflexive Banach space. Then, if Xn n is equal to 1 to infinity is a bounded sequence, it's in X, then it has a weakly convergent subsequence. Weakly convergent subsequence. Okay, so the remark is if the weak convergence, this is the notation. So we will write that Xn converges weakly to X. Okay, so if Xn converges to X, then this will imply that Xn will converge weakly to X. But it is possible that Xn may converge weakly to some X, but Xn this may not have. Okay. So in the Banach space case, or in our case, the substitute is the weak convergence. If you have a bounded sequence, then you will be able to extract a subsequence which is weakly convergent. The only thing which you require is that your Banach space need to be reflexive. Okay, so it cannot. So this is one substitute. Okay, and this is a reflective Banach space. Okay, now the question is that, for example, if you see here in my discussion before here, so I am having second property. If Xn has a convergent subsequence, Xni converges to X0, then another condition was that here limit I should be able to take it inside. Okay, that means it is continuity. But if I have a sequence which is converging only weakly, then I need this continuity with respect to that weak topology. Okay, so that gives me a definition. Okay. So let f is from say x to r. Okay. Then we say that where x is a Banach space, we say that f is sequentially weakly lower semi-continuous. Sequentially weakly lower semi-continuous. Continuous if for every sequence Xn which converges weakly to some X. Okay? Okay. If every sequence Xn we have f of x is less than or equal to limit of f of Xn as n goes to. That means if Xn converges to X weakly, then f of x should be less than or equal to lim inverse n goes to infinity of f of x. Okay. So this is a function which is sequentially weakly lower semi-continuous. Okay. So that means it's a, if it is weakly continuous, no, if it is continuous, and then, but that does not mean that it will be continuous with respect to the weak topology, because a sequence converges weakly, that it doesn't mean that it is converges in the weak. Xn converges to X weakly, that doesn't mean that it converges in the strong topology. Okay? So what we have is, essentially what I am trying to say is that F is continuous with respect to the weak topology. Okay? That is a much strong requirement. And I need only at a sequence level this happens. So that is what I mean by sequential logarithm. If these two things are there, then I can somehow prove the existence of a minimizer. Okay? And then I have to make sure that somehow as minimizing sequence is found. For that, I
How are
need
you? Bye. Stop recording.
I need another definition. Okay? So I will see what do you mean by a function is coercive. Okay? So let X be a Banach space. Banach space and F from X to R, then F is said to be coercive if f of x goes to infinity as norm x goes to infinity. That means as we go to infinity, fx goes to infinity. This is the definition. Okay. Then in that case, we will say that f is said to be coercive. Okay. Now, so what I wanted to tell here is that now I can state a theorem, the main theorem, which gives you an abstract theorem which assures you the existence of a minimizer. Okay. So that is what I wanted to do now. So let X be a reflexive Banach space. Let X be a reflexive Banach space and F from X to R be coercive and sequentially weakly lower semi-continuous. Weakly lower semi-continuous. Then F is bounded from below. F is bounded from below and attains its minimum. Or in other words, F is going to have a minimum. So this is an abstract theorem, okay, which we will be able to apply in our PDE course. I will indicate how we will do that. Okay. So what it says, what are the requirements? Let X be a reflexive Banach space. Banach space should be reflexive, and the function should be coercive. That means if you go to infinity, the function f of x should go to infinity. Okay, and it should be sequentially weakly lower semi-continuous. Okay, and once you have these kind of things, then f is bounded from below and attains its minimum. Okay, so this is the main thing. So the Banach space we are considering should be reflexive, and the function which we are dealing, it should be coercive. That means at infinity it should go to infinity, and the sequence, it should be sequentially weakly lower semi-continuous. That means if xn converges to x weakly, it should satisfy this identity. Okay, that is what. These are the conditions we. Then f is going to be bounded from below and it is going to attain its minimum. This is the abstract theory. Okay. So I will just prove it. It is not very complicated to prove it. Okay. So first I want to show that the infimum. Okay, so first let me take it that let m is equal to infimum of f of x where x is in the varies in the Banach space. Okay. Then we don't know right now, we don't know whether f is bounded from below. Then we only know that minus infinity is less than or equal to m, then which is less than or equal to f of x for all x. This is what we. So it could be minus infinity right now, okay, but we don't know. Now what I'm trying to do is that I'm going to extract a subsequence. Let xn be a sequence in x such that f of xn that converges to this minimum value. Okay, I'm taking a sequence in x such that f of xn converges to this minimum of f. Okay, so if m is minus infinity, f of xn will goes to minus infinity and whatever be it. Okay, so finally we will reach a conclusion that m is not going to be minus infinity. Now note that say as x goes to plus infinity, f of x goes to plus infinity. Okay, and this each fx is finite here. Okay, so note, and since m is strictly less than infinity, you will see that this implies that xn's are xn. Note that xn is a bounded sequence. Okay? Or in other words, you have this Banach space. Okay. So after a large ball, the f becomes very large. Okay. So the infimum, that minimizing sequence has to be somewhere inside, trapped somewhere here. Okay. That is because it is, as when x is large, fx is going to be infinity. Therefore, a minimizing sequence cannot go to infinity. So it has to be trapped somewhere in a ball. So this coercivity is used to get that the minimizing sequence is going to be bounded. Okay. So therefore, so that means what we have got is, that is, there exists a bounded sequence xn such that f of xn converges to m. This m is right now we know that it is greater than or equal to minus. Now, since x is reflexive, since f is reflexive and xn is bounded, and the sequence xn is bounded, there exists a subsequence. xni I equal to 1 to infinity, such that xni converges weakly to some x. This is in x. Okay. Now, therefore, since f is sequentially weakly lower semi-continuous, and xni converges to x weakly, what we will get is f of x. Okay. We know that this is if f takes real numbers, so it is minus infinity, strictly less than f of x. This is less than or equal to limit as I goes to infinity of f of xni. Okay. And we know that f of xn converges to m. So f of xni will also converge to m. That implies that minus infinity less than f of x. Yeah. And this is less than or equal to m. Okay. And we know that m is less than or equal to fx, so we know that this is also less than or equal to. So this implies fx is equal to m, and which is strictly greater than minus infinity. That implies that f is bounded from below, and it attains its minimum at the point x. It implies f attains its minimum at, and that proves the theorem. Okay. So this is what it shows, that if f attains its minimum at a point. So the main theorem here is, this is the main theorem if you want to talk about the existence of minima for a function in a defined on a Banach space. Okay. Now there are various conditions here we wanted to talk about. Okay. So f from x to r be coercive and weakly lower semi-continuous. Okay. So weakly lower semi-continuous, some remark, important example, one important example. One important example. So let x be a Banach space. Let x be a Banach space, and f from x to r be the function f of x is equal to norm of x. Okay? Then this implies that then f is weakly lower semi-continuous. Weakly lower semi, or sequentially weakly lower semi-continuous. Okay. So norm is an important example of a function which is sequentially weakly lower semi-continuous. One generally proves this in a functional analysis course. Okay. So this is a very important example. Some special cases are, for example, some examples. For example, so if you are a function f from say Lp of say r or Lp of omega to r, right? So by f of a function u is equal to its Lp norm. Okay. Then this implies that if say a sequence un converges weakly to u, then norm of u, this Lp norm, is going to be less than or equal to lim as n goes to infinity, norm of un. Okay. So it's a norm. For example, yesterday we have defined the Sobolev space, we have defined the space H1 of omega, the Sobolev space. Okay. There were norms, like norm of u was something like integral over omega, gradient of u square plus u square to the power 1 by 2. And then this also will have the same property. If un converges to u weakly, then you will have again this norm of u is less than or equal to lim n of norm of un. You will have. And another example is, yesterday I also introduced the space h10 of omega, which was a subset of h1 of omega. There was an equivalent norm, something like integral over omega, gradient of u square to the power 1 by 2. Okay? So using this theorem, we will get that if un converges weakly to weakly in h10 of omega, then if this half you can remove, then integral over omega gradient of u square is less than or equal to lim n as n goes to infinity of integral over omega modulus of gradient of un square. Okay. So you can have all these kind of examples. So norms are one of the main examples of functions which are weakly lower semi. Okay. Now the question is now the aim. aim is to apply the above abstract theorem to PD. So can we do that? And I have seen that, for example, so if you remember, I had this problem like minus Laplacian of u is equal to f of x, u of x in omega, and u is equal to 0 on boundary. Then I had an energy which was defined E from say space x to r by E of u is equal to half of integral over omega gradient of u square minus integral over omega capital F of x u, where capital F is the primitive and where x was nothing but all u in C2 of omega closure such that u is equal to 0 on boundary of omega. Okay. So now the question is u is equal to 0 on omega. Can we apply our, so the question is, can we apply our theorem to conclude the existence of a critical existence of minima of E. So the first condition is that in the theorem is that it should be a reflexive Banach space. Okay, but unfortunate problem is that the problem is that the remark the spaces, all these spaces like the C2 of omega, C1 omega, C omega, there are many, these are all not reflexive, not. The space, all these spaces are not reflexive. Okay, so we want to find, so we cannot apply the above theorem in these spaces. It's a major obstruction. Okay, so therefore we cannot apply the above abstract theorem in the above PDE context. So another remark is that then that will make the question, for example, which are the spaces which are reflexive function spaces. Okay. The first example is that LP spaces. LP omega is reflexive. Defined only here. 1 strictly less than P, less than infinity. Okay. P equal to 1 and infinity, they are not reflexive. Then the second one is the space we define, say H1 of omega and H10 of omega. These Sokolov spaces, these are reflexive. Okay. So the idea is that somehow these are the, for example, LP spaces, the space Sokolov space H1, H10. These are all reflexive spaces. Okay. So that is what I wanted to see now, whether I can somehow instead of this energy, E was posed in this kind of a space. Okay. But this space is not reflexive, and so we cannot apply our earlier methods. But they are Sokolov spaces are reflexive. And if you recall yesterday, we have shown that we have defined the weak solutions as elements of Sokolov spaces. Okay. So the idea is that instead of directly looking for a solution for even for today's PDE, this PDE what I have written here, this PDE also, our first aim is to look for define what is a weak solution, and that weak solution will be there in the Sokolov space. Okay, so I will just define it. Okay, so definition, weak solution. Okay. A weak solution. A weak solution of the problem minus Laplacian of u equal to f of x ux in omega with u is equal to 0 on boundary of omega is a u. This should be in h1 0 of omega satisfying weak solution, a weak solution of minus Laplacian of u is equal to f of ux in omega with u is equal to 0 on boundary of omega is a function u in h1 0 of omega satisfying the identity integral over omega gradient of u dot gradient of phi is equal to integral over omega f of x u of x this into phi of x dx for all phi h1 0. So instead of finding directly a solution, you try to find a weak solution. Okay? And then, so the question is that, then I will make it as a remark here. Remark. If f is smooth, that means just now I assume that it's only continuous. Suppose we assume C1 or something like that. If f is smooth, then we can show that. Weak solutions are indeed classical solutions. So this I mentioned yesterday also. This part is known as the regularity theory. Okay, and that's a separate story. And so what we can do is that if we can somehow show that there is a weak solution, then that weak solution is going to be a classical solution. Okay, so that is the main thing what we can do. So therefore, in view of this, is enough to find weak solution. Now this weak solution can also be seen as the critical points of the energy. That is what I am going to do next. I'm just not going to prove it, I am just going to state as a theorem. So define say, and E from the Sokolov space h1 0 of omega to R by E of u, that is going to be equal to, in E of u is equal to half of integral over omega gradient of u square minus integral over omega capital F of x. Okay. There are some assumptions on f, etc. Where this f, small f, capital F, etc., which was defined before, there are some, we have to put some, you see, when you write something, you have to make sure that all these integrals are finite, okay? So for that, we need to make sure that these integrals are finite. That can be done by assuming some growth conditions on small f, which I started with, okay? So if you have something like this, then the theorem is that then E is differentiable at every u0 element of h10, any point in the domain, and the derivative dE at u0. Okay, this has to be a linear function, so it has to act on a phi, and that is nothing but integral over omega, gradient of u dot gradient of phi minus integral over omega. This is the small f of x u into p. Okay, this is u0. So now this is going to be the derivative of this function which is defined. Now once you have this, so the definition of a weak solution is this. This is the definition of a weak solution. That means the left hand side minus right hand side is equal to 0. That is precisely the derivative. So from here you will get as an immediate corollary is that, okay, weak solutions of the problem minus Laplacian of u equal to small f of x u in omega with u is equal to 0 on boundary of omega. Weak solutions of the problem are precisely the critical points of the energy E, which is defined from h10 of omega to r by E of u is equal to half of integral over omega grade u square minus integral over omega capital F of x. Okay. So the weak solutions are going to be the critical points of this energy, but this time energy is defined in the Sobolev space. The earlier theorem was that classical solutions are precisely the critical points of E, which was defined on a space X, which was a subset of the subspace of the space C2. Okay. Now it is defined on a Sobolev space. Okay. Now the advantage is that now we can try to apply the now this H10, as I mentioned, is a Hilbert's it's a Hilbert space, and also what happens is that, for example, this guy, for example, it is going to be a norm square, and I already mentioned before that norms are weakly lower semi-continuous and so on, and also with respect to some other inequalities in this context. Okay, we can try to prove a theorem. We can prove a theorem that so I will just write it as a theorem. I'm not going the details because it requires a lot of time. So assume that f from omega closure cross r to r, okay, is continuous, and I have an estimate something like f of xt is less than or equal to some constant c1 plus c2 into mod t to the power p. Okay, mod t to the power p with p less than 1. Okay, with p less than 1. Okay. Then the problem minus Laplacian of u is equal to f of x u, with the u is equal to 0, this is in omega, and on boundary of omega, then this has a weak solution. It's a weak solution. Okay? So the proof is just by showing that in this case what happens is that E from, I can define from h10 omega to R, which is defined before. Then the first thing is that h10 of omega is reflexive, and the second one is you have to show that this E is coercive. Okay? This basically follows from the we can prove this using the growth assumption, using this mod f of xt is then or equal to c1 plus c2 into mod t to the power p, with p strictly less than 1. Okay? This will help you to prove that it is coercive. Okay? And then the E is weakly lower semi-continuous. E is sequentially weakly lower semi-continuous. Sequentially weakly lower semi-continuous. For that, you need this uses some inequalities in Sobolev spaces. Okay. I'm not going to the details, I'm just giving you an idea. So these properties are there, therefore you can apply the abstract theorem. So you can apply the abstract theorem. Okay. So with the help of that, you can prove that there is a weak solution. Okay. So that is the way you can try to prove an abstract solution. Okay. So in the remaining few minutes, I will just try to conclude. You see, there are many examples where you may not be able to prove that minimum excess. Okay. So what are the other kind of critical points you can think about? Okay. So the question is critical points other than critical points other than critical points other than local minima or local maxima. So one thing is what we know that, for example, even in R, for example, if this from say R to R, say f of x is equal to x cubed, right? Okay. Then x cube, it's 0, you can see that it is going to be here and x, okay? And x is equal to 0 is a critical point. It's a critical point, but it is not a local maxima or minima. Okay. And in fact it is a saddle point. Okay. So are there theorems, can you somehow find some theorems which captures these saddle points? Okay. So I just wanted to have, so for example, when you are talking about theorems which gives you a critical point, you should not forget about one of the basic theorem which you learn in your real analysis. Okay, what is known as the Rolle's theorem. What is the Rolle's theorem says that suppose f is from R to R, okay, which is differentiable, and suppose f of A is equal to some f of B for some A less than B, okay, then this implies then there exists a C in the open interval AB, such that f prime of c is equal to 0. Okay. This is a theorem. Rolle's theorem is one of the basic theorem you will see, which assures you the existence of a critical point. Okay. There are many ways of looking at it, and then you can have an abstract theorem in an infinite dimensional space, what is known as a mountain pass theorem. Okay. I will just state the theorem and just for your information. Okay. So we cannot do these things in details, just for a theorem. What is known as the mountain pass theorem. Mountain pass. So let X be a Banach space. Let X be a Banach space and f from X to R be a C1 function, whatever be it. It's a differentiable at every point and the derivative is continuous. C1 function satisfying the following points. So the first one is f of 0, I will assume that's 0. Okay. And f of some point x naught is less than or equal to 0 for some x naught not equal to 0. For some x naught, it is not equal to 0. And the second point is that there exists an R such that 0 less than R less than mod x naught, and there exists an R such that, okay, such that infimum of f of x for mod x norm x is equal to R. This is equal to some m which is greater than 0. And there is another condition, what is known as the f satisfies what is known as the Pallas-Mail condition or PS condition. And if you have these conditions, this implies that then f has a critical point. Then okay, let me then f has a critical point. Okay, f has a critical point. In fact, what it says is that yeah, maybe I will explain because I don't have much time left, only 2 minutes. Okay, so what it says is that I will just critical point. So I will just leave, this is my Banach space, let's see. Okay, and f is at this point f of 0 is 0. And I have another point here, x naught, where also f of x naught, this is less than or equal to 0. Okay. Now what it says is that I have a ball here, which separates this 0 and this point, such that on this f is greater than or equal to some m, which is strictly greater than 0. Okay. And then there are some conditions that satisfy some Pallas-Mail condition, which tells you that if for a sequence f of xn is bounded and f prime of xn is goes to 0, then that sequence will have a convergence subsequent. It's kind of a compactness condition. I don't have time to go to this. Then what you have to do is that you take some curve joining this point to this point. I will call it as a gamma. Okay. Then what I can do is that I can take f of gamma t. Okay, t is the time. Take the supremum over all such t. That means supremum of f over this curve. Then what you do is that you take the infimum over all such curve gamma. So you will have another curve here. And this will be some number, say I will call it as some alpha. Okay. Then what it says is that this this is alpha is called a mountain pass, and then this alpha is going to be what is known as a critical value. In other words, there will be an x naught such that df of x naught is going to be 0, and f at x naught is going to be equal to alpha. So why is it called a mountain pass? Because you can see it as, suppose my f was the height function, okay? So then f of 0 is 0, saying that 0 is at a height 0, and x naught is at a height less than 0. And here something is there where f is greater than or equal to m means, you can imagine there is a mountain where the minimum height is greater than or equal to m. So what it says is that now this condition, that is what is the supremum over Tf of gamma t, that says that if you take any curve, what is the maximum height which you have to climb on this to reach from here to here, it's x0 to x0. Now you look at the smallest such path, or the path for which you have to climb the minimum. Okay, when you do such a value, then that will end up with a critical point. So the path from joining from here to here, for which you have to climb the minimal height, that is going to be the mountain pass. That on that you will have a critical point. That's basically the content of the theorem. Okay, so I don't have the time to go into the details. Okay, and so just try to understand that in PDE, one way you may be able to find critical points by looking at the minimizers, and most of the times it's not possible. You have to look for saddle points, and there is one theorem which in some sense generalizes the Rolle's theorem to infinite dimensional spaces, is what is known as the mountain pass theorem. And there are more general theories are there for this, what is known as Morse theory and so on. Morse theory, and there are various things. There are more sophisticated math attached to these kind of things, and of course you have to study quite a bit of things to understand this. It's just a general introduction, okay? And I will stop here, and if you have any questions, I'll try to answer. Thank you.
Hello sir, thank you so much. I have a question. Basically, I want to ask you that what is the difference between locally compact and relatively compact?
No, you see, locally compact is, you see, basically you take any point, okay, and then
Yes.
it will have a neighborhood which is compact, okay. And I don't know what is relatively compact. I don't know what exactly is that.
Okay. And sir, one more question is that why do we need different types of derivatives such as Freset that you mentioned today's lecture, and Gatto derivative, and what is their significance and usage, like when we particularly use these kind of derivatives?
You see, you see all these derivatives, Gatto derivative basically make sure that directional derivatives exist. Okay. So even f is from, so for example, some R2 to R, okay, R2 to R, you take a point somewhere here. It is possible that directional derivatives, that is in all directions,
Sorry sir, your screen is not visible.
Okay.
Whatever you have.
Is it visible?
Yes sir.
Yeah. So you take, for example, a function f is from say R2 to R, okay, and you take a point here. It is possible that all the directional derivative exist, okay, but f may not be even continuous. Okay.
Okay.
So Gatto derivatives only make sure that there are directional derivatives exist. Okay. And Freset derivative is a notion of the total derivative, the full derivative. Okay. So, so the point is that, so Freset derivative implies Gatto derivative. Okay. So that means, you know that when something is differentiable, then all directional derivative will exist. And in fact, you can calculate the directional derivatives from the Freset derivative. Okay.
Okay.
But the full derivative may not exist. Even in practice, For example, when there are certain other types of PD, even the PDs which I am talking about, when there are cases, for example, your functional is not going to be the Frechet derivative, okay? But in some cases, you will get that they have Gatho differentiable, and the solutions are weak solutions, or solutions are going to be just the all points where all the Gatho derivative vanishes, okay? Yeah. So the message is that Gatho derivative is basically the directional derivative. Okay.
Okay.
And Frechet derivative is the full derivative. Okay. So in the Rn itself, you must have seen a theorem which tells you that if partial derivatives exist and if they are continuous, then it is differentiable.
Yes.
You can also have a similar theorem here that Gatho derivative exists, and if the Gatho derivative is continuous, then it is going to be Frechet differential. Okay. So application, there are many PD context itself, there will be many examples which may not be Frechet differentiable, but they are Gatho differentiable, and they are going to the ones which are going to be the solutions of the PD.
Okay, sir. Thank you so much.
Any questions from the offline participants? So on behalf of the Department of Mathematics, I thank Sir for giving us a wonderful lecture series, 4th session series. We learned a lot about Hilbert spaces, Banach spaces, and other aspects of PDE. Thank you, sir.
Okay, thank you. Yeah.